welcome to our today's lesson. We want to talk about the laws of conservation of momentum. Now, we have been able to look at the laws of motion. We have come across different parameters that we have related with each other. For example, we talked about inertia in our first law, where we said there is that reluctance to change the state of motion. But in our law 2, we were able to establish that we can offset that balance. We can actually offset it if we choose to introduce an outside force, external force, so that it could act on our body to cause some motion or to hold motion. Now, we considered momentum at that point, and we said that linear momentum is actually the product of mass and velocity. Linear momentum refers to the product of mass and velocity. Refers to the product of mass and velocity of a body. Now, there are instances where we could change momentum of a body, and we agreed that being a product of mass and velocity, the only way in which we can achieve change in momentum is if we changed the velocity. If we changed the velocity of an object. Now, we considered impulse, and we said that impulse, which is given by force times time, is equal to the change in momentum. Change in momentum is equal to the change in momentum. I want us to consider some two bodies and probably say that they were actually attached. The bodies were actually attached to each other like this. Let us give this one mass M1. This other one, we give it mass M2. Then we could use a spring to attach them. Now, when these two bodies are attached, they behave as a unit. When they are attached, they behave as a unit. Now, let us consider an explosion. of these bodies that they were attached, something happened to the spring so that now they were suddenly detached. That one means that they will separate and move in opposite directions, but with different velocities or even equal velocities, but in different directions. Now, remember our bodies have masses m1 and m2. Now, we are saying that they have been detached. So, each one of them has now started moving independently and has acquired its own individual momentum. So, let us talk about their momentums after the explosion. After explosion, momentum will be m1 v1, while the momentum of the second one will be m2 v2. That we consider after an explosion, m1 acquires a velocity v1 in one direction, while m2 acquires v2 in an opposite direction, for example, in an opposite direction. Now, suppose the explosion, takes time t. Suppose the explosion takes time t. Now, there are a few things we can be able to say about those two bodies. Note, initially, the bodies were attached using a spring. Now, something happened to the spring so that now the bodies were detached. Each one of them moved in separate direction, acquiring different velocities. Now, the first thing we can talk about is the momentum after collision. Momentum after collision is given by. Now, for m1, we will have the product of mass 1 and the velocity it acquires. Let us take the first direction to be positive, so that now we will add momentum of the second body, but note that the velocity is going to be in a separate, different direction, and vector quantities direction is very, very important. For vector quantities, direction is important. Therefore, if we take the first velocity to be positive, then we should take the velocity in the opposite direction to be negative, so that now this will be the momentum after collision minus m2 v2. But we said for that state of motion to be changed, there has to be a force that acted on the bodies. Therefore, the force caused an impulse during the time that it acted upon the bodies, so that impulse now will be given by Ft for body 1 and negative Ft for bodies 2. Body 2. Therefore, if we add the impulse plus negative of Ft is supposed to give us the change in momentum, which is m1 v1, and this one we subtract m2 v2. Now, we resolve the left hand side so that now we get 0 being equal to m1 v1 minus m2 v2. Therefore, from our equation, we can now formulate that m1 v1 is actually equal to m2 v2, which means that for this system of ours, momentum does not change. It is actually equal before and after an interaction. Now this brings us to the law of conservation of linear momentum, which you could write as so. This one is the numeric version. Now, suppose we have more than 2 bodies. For example, you could consider 2 bodies of mass m1 and m2 with initial velocities u1 and u2. Consider those 2 bodies. The bodies have different masses, which we are calling m1 and m2. Now, these bodies this time are not at rest, but they are in a state of motion, whereby mass m1 is moving at a velocity u1, while mass m2 is moving at a velocity u2. Now, after collision, they acquire velocities v1 and v2. Now, we want to come up with an equation of this state that will help us to conserve our linear momentum of these two bodies. Now, we are saying that the bodies have masses m1 and m2. They are in a state of motion where each one of them is moving at u1 and u2 respectively. Now, when they collide, they acquire, after collision, they acquire new velocities v1 and v2. We are asking ourselves, is there a possibility of conserving momentum in this case? And the answer is yes. That whatever happens, even if you consider one body which fragments into different parts with different momentums for each fragment, then momentum before collision will always be equal to momentum after collision. Therefore, for this our case, we write that by the law of conservation, of linear momentum, then m1 u1 plus m1 u2 will be equal to m1 v1 plus m2 v2. By the law that we have just looked at, the law of conservation of linear momentum, momentum before collision is always equal to momentum after collision. Therefore, if you add the totals before, they should give you the totals after collision. Now, let us state the law in words. We can state the law of conservation of linear momentum in words, and it states that for a system of colliding bodies, it states that for a system of colliding bodies, momentum remains constant. Momentum, remember, what we're interested in here is linear momentum. It remains constant so long as no external forces act. If our body is not acted upon by external forces, then momentum is always constant. Now, We can also talk about collision, get into the details of collision, and after collision, or when bodies undergo collision, when bodies undergo collision, we could have three different results from those systems. Now, one of them is that bodies could fuse and move together as a unit. Number one is that bodies could fuse and move together as a unit. For example, you could have two pieces of plasticine, and then you could have two pieces of plasticine, and then you knock them together. What happens is that they stick to each other. That is what we talk about as fusion, that they fuse, they merge, and they move together as a unit. Number two, they could separate and move in different directions at whatever velocity. After collision, the body could separate, like the case we have just had. The body separated and moved together and moved in different directions, depending on the force that causes the collision. That will inform the velocity that is going to be realized after collision. Now, the last result that you could achieve from a collision is that of bodies separating and moving in the same direction. They could separate but move in the same direction. Those are the three possibilities that you could expect from a collision. Now, this brings us to types of collision. This brings us to types of collision. Types of collision. And number one is what we call elastic. Is the elastic collision. Elastic collision. And for this type of collision, which we are calling the elastic, here is where both kinetic energy and momentum are conserved. Both kinetic energy and momentum are actually conserved. What do we mean? We have looked at 3 results that can come about when a collision takes place. Now, one of them we said that bodies could fuse and move together as a unit. The other one we said they could separate and move in different directions, or even they could separate and move in the same direction. Now, depending on the reaction of the bodies, kinetic energy and momentum are preserved. So this one is a case where bodies separate. They either move together or they move in different directions, but separately. They move independently at different or even the same velocities or even in different directions, but they do not merge, they do not fuse. Now, suppose we have 2 bodies of mass m1 and m2 moving at velocities u1 and u2. Now, after collision, the bodies acquire velocities. They acquire velocities v1 and v2 respectively. That we have our 2 bodies, m1 and m2. Those are the masses. We do not want to narrow down to figures. Now, they are in a state of motion where body m1 is moving at an initial velocity u1. Body m2 is moving at a velocity u2. Now, after collision, these 2 bodies acquire new velocities, which are calling v1 and v2 respectively. Now, by the law of conservation of linear momentum, by the law of conservation of linear momentum. Remember, linear momentum is given by mass, the product of mass and velocity. Now, initially, body m1 acquired a momentum m1 u1, and body 2 acquired m2 u2, which is now the initial momentum of body 2. Now, the total initial momentum will be given by the sum of the momentum of body 1 and that of body 2. Now after collision, M1 acquires a momentum m1v1, while body 2 acquires m2v2. So by the law of conservation of linear momentum, the totals before collision should be equal to the totals after the collision. That one is what we call the law of conservation of linear momentum. But we also said that in this case, we are also conserving kinetic energy. Recall, we said that kinetic energy is given by a half mass you multiply by the square of velocity. So in our case here, by the law, this is part B, by the law of conservation of kinetic energy, by the law of conservation of kinetic energy, for M1, kinetic energy before the collision was a half m u1 squared. We add that to a half m u2 squared. This is the total kinetic energy before collision. But we are saying after our bodies collided, they acquired some new velocities and for which kinetic energy needs to be preserved. So this one should be equated to the total kinetic energy after collision, which is given by a half mv1 squared for body 1 plus a half mv2 squared for body 2. So for this case of elastic collision, kinetic energy and momentum are preserved, which means that we can come up with these two formulas for the conservation of the parameters of our interest. We could also look at another type of collision, which we call inelastic collision. And here, for inelastic collision, linear momentum is conserved, but kinetic energy is not. That is the only difference that exists between the two. That for the first one, we are conserving both momentum and kinetic energy. But in this case, we are saying that kinetic energy is not going to be preserved or conserved. Now, why do we say that kinetic energy is not going to be conserved? Now, in this case, bodies here, bodies fuse and move together as a unit. Bodies fuse and move together as a unit, And therefore we can come up with the following characteristics of inelastic collision. Characteristics of inelastic collision. Now that bodies are fusing, the total mass is given by sum of individual masses. That is characteristic number 1. That now that the bodies have fused, before collision, bodies were very independent, but after collision, they have merged to move together as a unit. Therefore, the mass after collision is going to be considered to be the sum of individual masses. Now, number 2 is that bodies end up with common velocity. They have merged to form one body which is in motion. Therefore, the velocity after collision is just going to be the velocity of the unit mass, which is actually the sum total of individual masses. Now, when the fusion is taking place, some energy is going to be wasted when the bodies are being deformed. That is why we are saying kinetic energy is not conserved, because some energy is going to be lost during deformation. And number 2 is that some energy could be changed into heat, light, or even sound. Some bodies will collide and make a sound. For that sound to be produced, some energy is going to be involved. Same case applies to heat, same case applies to light. So if somebody asks you, why is kinetic energy not conserved? Number 1, energy is lost during deformation. And number 2 is that some energy transforms to heat, light, or sound. Some energy transforms to heat, light, or even sound. Some energy transforms to heat, light, or even sound. Let us now write down the equation of conservation of momentum. And again, we are going to consider two bodies, M1 and M2. Now, these two bodies moving at velocities u1 and u2 after collision. acquire velocity v1. Remember we said they are merging to form a unit and they end up with a common velocity. It is very important to understand that now, after the collision, we are having a unit body whose mass is the sum total of the two, and the velocity is common. Now, by the law of conservation of momentum, by the law of conservation of momentum, therefore, we could look at it this way. We have the two bodies, we have their initial velocities, we have the final velocity, which is common, and it's achieved after the collision. Now, by the law of conservation of momentum, momentum before is going to be given by m1 u1 plus m2 u2. That is the momentum total before collision. After collision, the mass becomes m1 plus m2, like that, m1 plus m2, and this one we multiply by v1, which is the common velocity achieved. And that takes care of the two characteristics we have just looked at, where the final mass is the sum total of the two, and they end up with a common velocity, which we have called v1, velocity v1. Now let us take an example. Now, the question reads, a body A of mass 5 kgs moving with a velocity of 3 meters per second collides head-on with another body B of mass 4 kgs moving in the opposite direction at 6 meters per second. After the collision, the bodies move together, and we are supposed to calculate the common velocity. Probably we can add that they move together as a unit. They move together as a unit. Then the question requires us to get the common velocity. The common velocity. But remember that momentum before collision equals to momentum after collision. After the collision. Now, we have been given our masses. M1 has been given as 5 kgs. M2 has been given as 4 kgs. Now, initial velocities U1 is given as 3 meters per second, and U2 is 6 meters per second. Now, after the interaction, we are told they move together. They move together as a unit. Now we are required to get the common velocity achieved. But now we can take momentum of body A. For A, momentum is going to be given by 5 times 3. 5 times 3. These are Newton meters per second. For our body B, momentum is given by 6 times 4. 6 times 4 newtons meters per second. Now, this is the initial momentum of the individual bodies. But again, you note that A is moving in a direction that is opposite to the other one. So we could also take our body B to have a negative momentum for us to take care of the direction. Therefore, total momentum before will be given by 15 plus negative 24, which gives us negative 9 kilograms meters per second. Now, after collision, the bodies fuse and move together as a unit. Therefore, momentum will be given by the sum of their masses, which is given by 5 plus 4. And this one we multiply by the common velocity that is going to come about after collision. That we said momentum after collision is given by a sum total of the masses and the common velocity that is achieved by the merged bodies. Now, but momentum before is equal to momentum after collision. Therefore, -9 kilograms meters per second, which is our initial momentum, should be equated to 9 kilograms V. Now, we want to get the value of the common velocity achieved. Therefore, we divide by 9 kgs and by 9 kgs, so that now our velocity becomes -1 meters per second. Why negative? Because we had two bodies, A and B, each moving at in different directions. We took the second body to be moving in a negative direction. Therefore, the common velocity that is achieved is in the direction of movement of body B, direction of motion of body B. Negative because it's a vector quantity, we want to take care of direction. Therefore, for elastic collision, bodies will separate and move separately, but for inelastic collision, they merge, and therefore we have two characteristics that are key in this case. One is that the mass is the sum total of the individual masses, and now that we have a unit mass, V is common. V is common. That's about all for Newton's laws of motion. I hope you have understood, and next time we meet we will start on heat. Thank you.